Hello, everyone. Looks like we're live. And my name is Deborah Byrd. I'm here with C. Alex Young. We are both with EarthSky. Alex is also with NASA Goddard Space Flight Center, and he's a heliophysicist, which means that he studies the sun for a living. Cool job, Alex.
Thanks, I love it.
So we're here with the sun news of the week. And as you can see, we're going to be talking first about how Earth eclipsed the sun this week. Natalia, could we get the next slide? We'll show you that eclipse. Okay, so what's going on here?
Yeah, so these are actually some of my favorite images. So these are extreme ultraviolet images of the sun from the GOES spacecraft. And much like the SDO or Solar Dynamics Observatory, they have special orbits they're called geosynchronous orbits. And they're in, because of those special orbits, they're in them in order to give the longest uninterrupted look at the sun. But the downside that you have to make is that there is a short period of time, twice a year, where these spacecraft experience what we call eclipse season. And so during that time, there's a period during the day when the Earth basically gets in the way because the spacecraft are down low enough that they're actually looking through the edge of the Earth's atmosphere at the sun. And then eventually the Earth kind of moves in the way and blocks it. And so that's what you're seeing is you're seeing the shadow or you're seeing the shadow of the Earth that's cast onto the spacecraft for via the sun because of this particular observation. And one of the things that you pointed out is you notice that those little edges, they're not nice and sharp and smooth. The shadow edges are not sharp and smooth. For example, when we see a solar eclipse, the edge of the moon is very sharp because it has no atmosphere. But here, we're looking through part of the atmosphere, and that's what makes that shadow kind of fuzzy as it moves in front of the sun.
So what we're looking at here is just one event, and all these different colors of the sun and so on, those are just different wavelengths, right?
Right, right. And these are actually wavelengths. This is the same for the Solar Dynamics Observatory. Most of the wavelengths are not wavelengths that you and I can see with our own eye. They're not visible wavelengths. They're much like X rays or ultraviolet, they're in between those two. But so the images are actually made with a special camera and they're actually grayscale. They're basically black and white kind of images. We color them ourselves, and we do that for two reasons. Number one, we color them so that the longer wavelengths are more reddish because on the visible spectrum, red is the longest wavelengths. And then as you move to the shortest wavelengths, they get more blue. And so that's what we do with these in order to sort of follow that convention. But we also pick these color tables, we call them. We pick them so that they kind of accentuate certain features in those particular wavelengths that we know are there. And they make it easier for us to see things like filaments that we've talked about, or prominences, or coronal holes, or even solar flares.
Yeah, because every time we're looking at a new colored image here, we're seeing different stuff.
Right, because that's the other thing that's kind of crazy is the sun is got sort of a very bizarre atmosphere. So the outer part of the sun is its atmosphere because its atmosphere is super hot flowing away. That's called the corona. That's the part that we actually see during a total solar eclipse. And the crazy thing about the corona is as you go up, it gets hotter, not cooler as you would expect. And so, when it gets hotter, the wavelengths actually get shorter because they're more energetic. The hotter something is, the more energetic the light, therefore, the shorter the wavelength. And that's what's happening here. So you're looking not only at different things, but you're looking at different layers of the sun's atmosphere.
And so this event that we're looking at is just one event that happened on the sun on one day. And
Hmm.
it looks like the day, looks like it was
The
September
18th.
the 18th, September
Yeah.
18th. And so the spacecraft, the Earth came between the spacecraft and the sun. So that's the Earth. What we're seeing pass across the sun there is the Earth.
Right, right. Yeah, it's kind of crazy.
It is kind of crazy. And so this is the GOES spacecraft,
Hmm.
GOES. And there's another spacecraft, Solar Dynamics Observatory, CEDO, that does this too. And they call those eclipse seasons.
Right, right. Now, we do actually see sometimes the moon move in front. And those are not the eclipse seasons. Those are, we call those lunar transits because they don't happen on this schedule like these eclipse seasons do. They're not completely random, but they're a little bit, spread all over the place because actually the moon itself has a very, compared to other things, the moon has a fairly complicated orbit, which is what
Right.
makes things like solar eclipses so exciting because they're a little bit more rare because they don't happen every month.
Some really smart people figured those out.
I know they
You
figured it out,
know,
and they figured it out hundreds of years. Well, actually, some people figured out parts of this thousands of years ago.
thousands of
Now,
years ago.
we didn't start having nice detailed maps of them actually until Halley. So, Halley of Halley's Comet. Sir Halley was a very famous astronomer, physicist in England, and he was the first person to make a fairly accurate map, and he made it using the principles of gravity and orbits that Newton and Kepler were the ones who came up with, and Newton's universal law of gravitation. But the actual geometry, figuring out, because it's just geometry, you've just got these balls, and they're, depending on where they are, there's always a shadow cast by the moon, for example, from the sun.
Somewhere.
However, that shadow is somewhere in space. Well, we want to know when it goes over the Earth, but that geometry is really, really complicated, and so you can't just put down some equations and do it exactly. Well, there was a very, very smart man named Bessel, and people may have heard of things like Bessel functions. Bessel figured out a very, very straightforward, simple geometry by making certain assumptions. That's what we've used for couple hundred years now to actually calculate the location of eclipses. Now there are other factors that we've used to make our calculations more accurate, which maybe we could talk about in another time. It's pretty interesting stuff. But it's pretty amazing that he figured that out before we had computers. People just, they had to do it by hand.
And when was that? That was probably like the
That was
1800s
in the
when,
1800s. Yeah, I
yeah.
honestly can't. I think it's the mid 1800s. I can't remember the exact date, but yeah, it's 1800s.
And so can you imagine what Bessel and Edmund Halley of Halley's Comet fame, can you imagine what they would have thought if they had seen this image?
Oh, I'm sure they would have blown their mind. I
It would have
mean,
blown their minds.
yeah, I mean, honestly, actually, the first time I saw these kind of images, which were from the SOHO spacecraft, kind of the previous generation, I was completely wow. They are super amazing images.
They are. I was amazed by them too. So let's have the next slide, Natalia. And I wanted to show this. Alex, you sent this to me yesterday.
Yeah.
These are the spacecraft that we have pretty much right now, pretty much all of these, because this is
Hmm.
from, I think you said last year, this.
This is from last year, but it is all the current spacecraft that are either in orbit, uh, in space, or that are in development. So there's several
Oh,
here,
okay,
for
in
example,
development.
that are in development. Yeah. For example, I'll just point a few out:
But
IMAP and
wait,
Punch.
let me say
Okay,
one thing before you do. These are
sure.
the just the spacecraft that are studying the sun.
Right. And
These are
and
the
let me
sun
Right.
spacecraft.
And let me clarify that a little bit. Helio does mean sun, but heliophysics is actually a little bit more than that. So it kind of starts at the sun, but really it's the sun and how it interacts with everything. Um, and we've even expanded that a little bit because there's upper layers of the Earth's atmosphere that interact with the lower layers, things like where the aurora occur. And those are very important, not just for heliophysics, but also for earth science. And that is really kind of become an area of heliophysics. And that's what we're trying to show here. Basically, if they're kind of sitting out in front of the earth, between the earth and the sun, they're either looking at the sun directly or they're looking at all the stuff coming off the sun.
Right.
Um, and
And
you
so,
see ones that are around the earth are all generally looking at what's happening at the earth.
right. And so we're looking here at the sun, of course, the big red ball on the left, and then the Earth is sitting over there, kind of more to the right. And then they've in this illustration depicted the Earth's magnetic field because that's
Right.
so important in that sun-Earth interaction. And could
Exactly.
you speak about that a little bit?
Yeah, so that's a very important part because you'll actually notice in the bottom right they have Mars
Oh yeah,
because Mars
Mars.
actually yeah, Mars actually has a radiation detector on the Curiosity spacecraft, a Curiosity rover. But you'll notice Mars doesn't have a magnetic field because Mars doesn't have a global magnetic field like the Earth. The Earth has what we call a global magnetic field. It can be quite complicated, but it's basically like a giant bar magnet. The Earth is a giant magnet that has a north and south magnetic pole, and that magnetic field interacts with both the atmosphere of the Earth and all of that stuff coming off the sun. And that has huge, important implications. For example, that's part of what creates these huge, what we call geomagnetic storms that then create aurora. Um, but they also have impacts on our technology. That layer of the atmosphere is very, very chaotic and dynamic, and it changes. And when it does, due to what's happening both at the sun and at Earth, it actually impacts our communications. The satellites that give us things like GPS, certain radio frequencies that are important for airplanes and ships, those are impacted by this crazy interaction that's driven by the sun and the Earth's magnetic field. And that whole field, that is the understanding of what's going on, is something we now call space weather. This
Right.
is an environment in space created by the sun interacting with other things in the solar system, and that's space weather. And so heliophysics, part of heliophysics is the study of that interaction called space weather.
Right. And we spoke a couple of months ago with Sean Dahl, who is a space weather forecaster
Hmm.
with, I don't remember if he's with NASA or
I
NOAA. I
think
kind of
he's
think he's with,
Noah. Yeah,
I think
he's
he's
Noah.
NOAA. And
Yeah.
so one of the things that we talked about, and if you look at EarthSky's live stream area, you can find that interview with Sean Dahl where he's talking about the hotline that's used. So whenever there are big flares on the sun, that
Hmm.
now space weather forecasters like Sean and heliophysicists like you, Alex, have this system for alerting the power grids that
Hmm.
there's going to be a big solar storm, and so that's worked so far this year. We haven't had any
Yep.
major. It's been, even though we're pretty much at the peak of the solar cycle 25, we haven't had any big power outages. So that system that has been put together by people of goodwill seems to be working.
Yeah, I
So
think it's a great statement of the success of that. NOAA is the official forecaster for the nation, and they are directly connected to them, and they work very closely with NASA, with this, in particular, what's called the Moon to Mars office, which is what does a lot of the same sort of work for NASA and their astronauts and their spacecraft. And those two organizations work very closely together.
yes, and so we still have a lot to talk about here. So let's move to the next slide.
Yeah, at some point we should come back to this and talk about what those some of those different missions are. I mean, we could talk about it for a long time. I will say that one of the things we call that, you can still go to the next slide, but one of the things we call that is the Great Heliophysics Observatory. So all of those pieces, we think of them as one giant observatory to give us the broad perspective of what's happening in our solar
Oh,
system.
that's so cool. That's awesome. Yes, we're going to do that. But maybe we need to do it at a time when the sun is not so active
That's a good
because
idea.
we are, we are in a place right now where the sun is very active. So the sun has its 11-year cycle, and we're now close to the peak of that. And so here's something that happened on the 14th. So I think that was Sunday, where we had an X 4.5 flare, and this is not an animation. This is the real sun. It's showing the flare occurring. So can you tell us
Yeah,
about that?
absolutely. So this is actually some data that I put together, and actually there are tools which we'll go over sometime. You can do this yourself. But what we're looking at here is data from the Solar Dynamics Observatory, or SDO. This is extreme ultraviolet, one of my favorite wavelengths. And what you're seeing, you see that bright flash. Okay, that's the flare. Flares are basically very intense, relatively short on the scale of maybe minutes, sometimes hours of light over the whole spectrum. Light we can see, light we can't, like X rays or also radio waves. But then you also will notice off to the left, there's this bright structure that comes out. Okay. And what that is, we've talked often about filaments. Filaments are these pieces of solar material that are strung across the sun. Sometimes those filaments will be across a sunspot region. And so when that happens, you can have a flare that then causes that filament to be basically set free. And that filament very quickly and violently flies off the sun. And that's what you're seeing here. And that filament,
I
once
see
it
it.
leaves the sun, yeah, you can see it coming off. And once it leaves the sun, we then call it a coronal mass ejection. So it's mass stuff, sun stuff, that has been ejected from the sun. And those coronal mass ejections, or of course, we all use these acronyms, CMEs. These CMEs are what cause the geomagnetic storms at Earth that give us the aurora, but that it can also impact our communications.
And this particular one, Natalia, let's get the next slide. This particular X-flare was especially interesting because it was so fast moving.
Hmm.
So
Hmm.
unlike this animation is kind of slow, but there it goes. It's
There it
starting
goes.
over. Okay, so this is just an animation. This comes from NASA's Scientific Visualization Studio. So this stuff leaves the sun, but then watch, a second piece runs into it. So that's what happened here. There was a flare on the sun on the 13th that was a smaller flare, and then on the 14th was the X flare, and
Hmm.
and the X flare sent out a CME that was moving faster, right? So tell us about
Right.
this
Right.
animation
So
and what
yeah,
happened.
so just a little aside, you don't always have a CME with a flare. However, when you have stronger flares like M and X flares, they're more common. And in this case, the M flare, which is M for moderate, that actually also had a CME associated with it. And it was relatively slow. It was going just a little bit faster than the background stuff coming off the sun. And then that X flare 2 days later, no, one day later, was much faster. I think it was maybe twice or three times as fast as the first CME. And that second CME overtook the first CME. Now, one of the names that we use is called the cannibal CME. And I'll tell you, there's actually a little bit of a controversy in the community. Some people don't like that name because cannibal kind of implies that one CME eats the other one. But really, what's happening is those two CMEs kind of combine into a much more complicated sort of more super CME. And that oftentimes the reason we're interested in that is when you have that effect happen, that boosts up the CME and they can often have a stronger effect. And that's
Hey,
exactly what we saw.
but isn't that eating? Like you eat something and it becomes part of you, right?
Well,
So
yeah, I personally like the name
me
because
too.
it's just easy to say. But I have some colleagues who are very, very good and very smart, and some of the better heliophysicists in this particular area, and they don't like that term. But it's okay. I think it's okay to use it. It was actually published in a paper by one of the scientists at Goddard Space Flight Center, Nat Gopalswamy. I think that was 2012 that was published, and that term caught on, and it's become fairly popular.
Well, I got to say that when I went to NASA's Scientific Visualization Studio this morning and grabbed this animation, the label on the animation was Cannibal CME.
Yeah,
so,
yeah.
so,
So
so,
it's that's the easiest way to find it.
Right, and I'm sure NASA's got those words everywhere.
Yeah.
So this is cool. So the big CME caught up with the little CME, and they combined, and they were headed to Earth. And let's have the
Yes.
next slide, and we'll see a result of that.
Well, not quite.
It's coming. It's
It's
coming.
coming.
Next slide,
Anticipation.
Natalia.
Anticipation.
Oh,
There
there
we
it
go.
is. So this image is by our own roving nature reporter, Kelly Kaiser-Witt, and she is actually just outside of her house on this one. She lives very far north in Wisconsin, and she can sometimes see the aurora. So tell us about this storm.
Yeah, so this was actually a pretty exciting event. It created, so we have a scale for all of these types of phenomena. We have a scale for geomagnetic storms, and that scale goes from 1 to 5. So we have G1 up to G5. And we also have a name associated with them. The names, I believe, are minor, moderate, strong, severe, and extreme. Okay. Extreme is what happened back in May when we have that amazing aurora that was seen all over the world, even very far close to the equator. This one we saw was a G4, so it was a severe storm, not an extreme storm. Um, and what that meant is that the stronger the storm, the farther south the activity in the upper atmosphere occurs, which means you can see the aurora farther south. Now, in this case, when you see it farther south, you can often see it on the horizon. It's not overhead and the super dynamic, but you can see the glowing on the horizon. And that's kind of what you see here. However, I will note that there is some structure. So it's fairly close. That she's not right underneath it, but she can see some structure, which means she's not too far, probably, hundreds of miles, but not too far from the really dynamic aurora that you often see from Scandinavia and Canada and Alaska. And the colors come from the kind of air, the parts of the air that the sun stuff, the particles coming down interact with. If they interact with oxygen, so let's remember the air we breathe is primarily nitrogen. It's almost exactly 3/4 nitrogen and 1/4 oxygen with lots of little things in there. And so nitrogen is actually not the most common color we see. The most common color we see comes from oxygen, which is the green and sometimes red. Nitrogen typically gives us a blue, sometimes a teal color. Those are a little bit harder to see. And those colors mix together. So what you're seeing here is somewhat a little bit of green. It's kind of pinkish, which means there's some red there, and that's what we're basically seeing when we see those colors in the aurora.
Hang on 1 second, Alex, because she has lost her feed, and I
Okay.
need to just jump on here
Okay.
and see if I can get it back for us.
Okay.
So, are we seeing that? Yes.
I
Okay,
see
hang
it.
on.
Yeah.
Hang on. I got to flip through these. There it is.
There we go.
Yep.
Yeah.
Okay.
So I think you can see some green, down lower, and it looks like some red higher up. And that's actually not. I mean, that's actually there are different effects that determine whether or not you see the green or the red. But one of them is that the typically when you're higher up, the atmosphere is thinner, and the reaction that causes the red is more common. So that's typically why you would see the red higher up. Now there are also some other reasons why you would see red, but that's probably got something to do with why the red is above the green.
So this is one of the beautiful things about sky watching in general, and but sun and aurora observing in particular, and that is, we had this event on the sun on the 13th, and then we had an even bigger event on the 14th, and then those two got together, and we didn't expect this large a response from Earth's magnetic field, but then we got this really good response,
Hmm.
and we got this G4 storm that created these beautiful colors. And that's awesome because we didn't know we were going to have that. So everybody was surprised. I know that I'm not usually on the EarthSky chat late at night, but I just happened to be on it that night, and I know that everybody was really excited about this. Everybody at EarthSky was really excited about it. So I keep forgetting that I'm the one that's doing these.
Okay.
Okay, so we have this image. I wanted to throw
Hmm.
that in there. Tell us about this image. This was also from this week. This was from the 15th.
Yeah, so this is another image that I made, and I made this one just because I really liked it. I thought it was very interesting. So this is actually right next to the region that created the X flare that we were just talking about. And what you're seeing, that dark material that you're seeing kind of in between the two bright patches, is a filament. That's the structure we call a filament. And when you look at a filament on the off the sun, off what we call the limb of the sun, we call it a prominence. But again, they're the same thing. It's just a matter of perspective. But the reason that I liked this one is you see things that are kind of swirling around, twisting, and that's indicative of the fact that what's controlling, what's dominating, what's happening here is the magnetic field of the sun. And magnetic fields, that they have some properties that are kind of like a string or a rubber band, and they get twisted up, and they can unravel, and in some ways you're sort of seeing this twisting, untwisting. And I thought that was really cool, and it makes that really neat effect, almost like a swirling. Sometimes we've actually called those solar tornadoes, because they have that kind of swirling like effect. But that's basically a filament that is an active filament. It's dynamic, and it's being driven by the magnetic fields on the sun.
So all this stuff that we've just talked about in the past 25 minutes, all this stuff happened this week
I
on the
know.
sun.
Yeah. And this was not even the busiest week that we've experienced. And it probably, I could be wrong, but it probably won't be the busiest one we see moving forward either. I expect that we'll probably see some additional weeks with some big flares, some big CMEs, and some big activity here on Earth. I certainly hope to see some aurora where I live in the mid-Atlantic.
Ooh, I hope you do. Oh, I know I'm
Yeah.
not going to see any down here in Texas, so I'm not
Well,
crossing my fingers.
you never know. It's probably unlikely, and there was certainly aurora seen during the May event. A lot of us, including myself, were clouded out by that, which is always the problem. But it could happen again. It could. It's less likely, but it could happen.
Okay, so Alex, thank you. It's been awesome as always. We're going to let the sun have the last word here. We thought you guys might enjoy this. We found this meme and we liked it a lot. We shared it on our Instagram page today, so you can find EarthSky on Instagram if you're looking. And people really enjoyed this. So I hope that everybody watching enjoys it too. And I hope I can figure out how to end us here because we've lost our producer, but I think I can do it. So bear with me, you guys. We're going to say goodbye and hopefully we'll go away. Ooh, that doesn't look right. Let's see. Oh, I
There's
think I
a
see it. I think I see
stop
it.
button.
The stop button. Yeah, you can't go
Yeah.
wrong with that. Okay, goodbye, you guys.
Bye.